Earth Engine API, and followed by a demonstration of a water quality analysis tool that we have built using the Earth Engine. And this would be followed by a hands-on session, by the end of which you should be able to create basic remote sensing applications using the Google Earth Engine on your own. So these are the topics that we would be covering for today's presentation. We'll be talking about what is the Google Earth Engine and how it works. We'll discuss why it is a powerful platform. We'll then talk how you can get started with the Earth Engine. We will discuss a few advantages and limitations of the Earth Engine. We will discuss a few applications of the Earth Engine, and then we will follow this up by the demonstration and hands-on session. So what is the Google Earth Engine? The Earth Engine is a cutting-edge technology that simplifies the analysis and visualization of geospatial data sets. So with the traditional methods, what you would have to do is first you would have to find the data that you want to work on. You would have to then download the data. You would then have to find the software that is required for processing your data. You would download that software, and then you could actually start with importing the data into your software, and then you would start with processing your data. But with the help of Google Earth Engine, you have access to a multi-petabyte repository of analysis ready data that is atmospherically corrected, radiometrically corrected, and geometrically corrected. So this is a cloud-based platform using which you can perform global scale analysis in just a matter of minutes. Using the Earth Engine, you can detect and quantify changes over the Earth's surface. You can generate statistics, charts, graphs, and even animations. So how does it work? At the Google Data Center, there are several storage and compute servers that store these data sets in the form of pyramids of tiles. Along with these data sets, many built-in primitive algorithms are stored, which are used to analyze these data sets. So when you want to send a request to the Earth Engine, you do it by writing a code. Your code can consist of several functions, which can range from basic mathematical operations to complex machine learning algorithms. So when you write the code and when you run it, your code gets converted into an object that represents a set of instructions. These instructions are then parallelly executed over multiple servers, and the result is reassembled and sent back to you as a single unit. So you get only what you asked for. If you want a chart to be displayed, all the calculations regarding that chart would be performed on the Google servers, and you would get back only the chart back to your browser window. This consumes very low bandwidth, and it is almost like having a supercomputer at your own desktops. So the Earth Engine is a powerful platform for a couple of reasons. The first of them being its wide public data catalog. So the Earth Engine hosts more than 40 years of satellite data in both optical and non-optical wavelength. It hosts more than 400 public data sets covering more than 20 petabytes of data, and more than 6,000 images are being ingested into the Earth Engine every day. Usually the time lag between the acquisition of an image and its ingestion into the Earth Engine is 1 to 2 days. That means if an image is acquired by a satellite today, it would be ingested into the Earth Engine by tomorrow, or certainly by day after tomorrow. This varies from dataset to dataset. The Earth Engine hosts data from the Landsat series at a 30-meter resolution. This includes both the top of atmosphere data and the surface reflectance data. It also hosts data from the Sentinel series, the SAR data from Sentinel-1, and the multispectral instrument data from Sentinel-2. It also hosts data from the MODIS series. Other than these satellite imagery, there are several geophysical datasets available on the Google Earth Engine, including the atmospheric data, land cover data, terrain data, sea surface data. So using these variety of datasets, you can perform varied calculations over the Earth Engine. You can detect changes in forest cover, changes in land use. You can study the changes in surface water over time. You can study diseases, disasters, and there's a lot that can be done using this tool. Other than the datasets that are already available, You can upload your own raster and vector files onto the Earth Engine and use the Earth Engine's tremendous capabilities to perform analysis on your own data. Another powerful feature of the Earth Engine is its processing power. So when you send a request to the Earth Engine, your region of interest gets split into multiple tiles, and each of these tiles are processed on a separate processor, and the result is reassembled and sent back to you. The Earth Engine also follows a lazy computational model, which means that at any point in time, only those many pixels are computed which are necessary to fulfill the current request. So depending upon your map's zoom level and the boundaries, the Earth Engine dynamically determines the resolution and projection of the output that is required. So it limits the calculation to only those pixels that are currently viewable in your browser window. The Earth Engine also has many inbuilt scientific algorithms which are optimized for use over parallel processing platforms. So this means that you need not write a code for every basic operation that you want to perform on the Earth Engine. The Earth Engine does it. The Earth Engine does it for you, and you can effectively use these algorithms. The Earth Engine also follows a judicious caching mechanism, which means that all the expensive intermediate results are stored in a cache memory, and when these values are needed at a later point in time, they need not be recomputed but can be directly fetched from the cache. In order to assess the power of the Earth Engine, the developers at Google performed certain experiments, and they concluded that the power of the Earth Engine depends less on the number of processors that are available, but more on the manner in which Google distributes the computation among these available processors. To quote numbers, they said that for 1,000 processors, the Earth Engine was able to perform calculation over 15 gigapixels in just 1 second. So we can all imagine the number of processors that would be available at the Google data centers, and 1,000 is just a very small fraction of it. Another powerful feature of the Earth Engine is that you can save and share your work routines. So you can import your own raster and vector data into the Earth Engine and you can work on that, or you can export your results to your Google Drive and eventually onto your desktops, and you can import them into any third-party application for further processing. The Earth Engine also stores your code. It maintains several versions of your code. At any point in time, you can compare your code with a previous version and revert back to a previous version if required. You can also share your code with other users, and this comes handy when you are working in a team or collaborating with others. And if you don't want to share your code, you can embed your output in the form of applications which are alike to both experts and non-experts. No code is shared here, and these are presented in the form of user interfaces which the user can interact with, and the user doesn't require any Earth Engine account in order to view or interact with an app. Another reason why the Earth Engine is so powerful are its interactive development platforms. So we have the Google Earth Engine Explorer, which can be used by non-specialists for viewing purposes, for visualization of the data. This has limited analysis capabilities. But then we have the application programming interfaces, which are far more powerful. The Google Earth Engine provides APIs in two forms, the JavaScript API and the Python API. The JavaScript API has access to all the Google Earth Engine libraries, as well as a set of user interface libraries that are provided by the engine. To use the JavaScript API, the user need not download anything. They do not need to have anything pre-installed on their systems. You can directly go to code.earthengine.google.com, sign up for the Earth Engine, and start using this on your browser. The Python API has access to not only the Google Earth Engine libraries, but a wide variety of Python libraries. However, here the user has to take care of visualization on their own, as the Earth Engine doesn't provide visualization libraries for the Python API. Both of these APIs have built-in geospatial tools to perform complex analysis, and they enable global processing with just a few lines of code. Knowledge of remote sensing or GIS is not a strict requirement in order to use any of these APIs. However, some scripting knowledge may be of use, but you keep learning as you start working on the Earth engine, and it gets more and more interesting with time. This is what the JavaScript code editor looks like. The region labeled 1 is where you write your code. This is where you write your scripts. The section that is labeled 2 is where you visualize your data. The region that is labeled 3 lists down all the scripts that you have created on the Earth engine. And the section labeled 4 is where you can view your outputs. So any print statements that you give within your code are displayed here. Let us discuss some fundamental data types that are come to use when we use the Earth engine. So we have an EE.image. So anything that starts with EE on the Earth engine is a server-side object, and everything else is a client-side object. So a server-side object is computed on the Google servers, and a client-side object is computed on your web browser. So an image is the most fundamental raster data type available on the Earth engine. Each image can be composed of one or more bands and usually has several metadata properties associated with it. The image metadata can be the time of image acquisition, the location of the image, or the percentage of cloud cover that is present in an image. An image collection is a set of related images. It is a time series stack of images. So if I refer to a Landsat 5 collection, I might be referring to the set of Landsat 5 images right from the first date of acquisition to the very last date of image acquisition. Then we have EE.geometry or EE.feature, which is the most fundamental vector data type on the Earth engine. A feature can represent a point, line, or a polygon. A feature collection is a set of multiple features. Let us discuss some basic functions and operators that we can use to analyze these fundamental data types. So the Earth engine provides the map function, which is a very powerful function. It lets you apply the same operation over all the objects in a collection. So this is basically like a for each loop. So if I have a set of 50 images, and if I want to apply NDVI over all these 50 images, then method 1 would be to take each image one by one and apply the NDVI formula over it. But this would question the very objective of programming itself. So here the map function comes to our rescue, and using the map function, you can compute NDVI for 50 images with just a single line of code. The number of images can be 50, they can be 100, they can be 1000. This number really doesn't matter. Then filters are provided by the Earth engine to enable you to restrict the scope of your analysis either temporally or spatially. So the filter helps you in selecting from millions of images, narrowing down your collection to the particular images which match your exact criteria. So if I have a set of Landsat 8 images, and let's say I want to study the images from 2019, that is from 1st January 2019 to 31st December 2019, then I'm restricting my collection temporally. And if I want to study regions of Delhi and adjoining areas, then I would be restricting my collection spatially. Several reducers are available on the Earth engine, which let you aggregate your data. They help you generate statistics from your data. Reducers like mean, median, max, min, standard deviation are available on the Google Earth engine. Several machine learning algorithms are available to enable you to perform supervised and unsupervised classification. You can also perform band math over the Earth engine. You can subtract one image from another. You can add a constant value to an image, and you can mask out individual pixels within an image. The Earth engine also provides UI widgets in the form of buttons, checkboxes, or drop-downs to make your application more dynamic and to enable the user to select the parameters that they desire and to perform on-the-fly operations on that basis. So in order to perform any operation on the Earth engine, there are a series of basic steps involved. Firstly, you would want to import a collection. This could be any of the collection available with the Earth Engine data catalog, or it could be something that you have uploaded to the engine. Then you can proceed with filtering your data, filtering the collection depending upon your time period of analysis or your region of interest. Further, you will proceed with performing the actual analysis that you desire. After this, you can choose to either display your results or export them to your Google Drive. Optionally, you can choose to create apps and share your work with others. Let us discuss a few advantages and limitations of the Earth Engine. So the Earth Engine should be used when you want data coverage for a large region. So if you want to study an entire country or even the entire world, the Earth Engine is the tool for you. Also, when you want to study data covering a large span of time, the Earth Engine is recommended to be used. Several studies have been conducted on the Earth Engine that have spanned more than 32 years of data. The Earth Engine should also be used for advanced raster processing. But when we come to the limitations, we see that the Earth Engine is not recommended for heavy-duty vector operations. As currently, the vector analysis capabilities on the Google Earth Engine are limited. The Earth Engine should also not be used when you want to influence the details of parallelization, because the price of liberation from these details is that you are unable to influence these values. So Google itself takes care of how your computation is managed, how your data is distributed, and how the parallelization is performed. You as a user have no control over these parameters. Let us discuss a few case studies that have been carried out using the Earth Engine. So there is the Hansen deforestation dataset, which is available on the Earth Engine and is used to track loss and gain of forest at a global scale. This dataset used nearly 7 lakh Landsat images along with a decision tree algorithm to map global forest dynamics. This dataset has data available from the year 2000 to 2019. On your right, you can see India and the Hansen deforestation dataset applied over it. And below that is the northeastern state of Assam. And we can see that the region in green are the forest areas and the red patches are where forest loss has occurred anytime in the past 19 years. The global surface water occurrence map is also available on the Google Earth Engine, and it is used for monitoring the change in intensity and occurrence of surface water. This has data from the year 1984 and was in fact the biggest science carried out on the Earth Engine. It took more than 2 years to arrive at this dataset. And this dataset, using this dataset, you can map the loss and gain of water at a global scale. Using the Google Earth Engine, we at IIRS have also developed a water quality analysis tool that uses Sentinel-2 multispectral instrument data as its base data. And depending upon the user parameters, it is able to calculate the water quality of any inland water body across the globe. So it takes Sentinel-2 data as its base data. It lets the user select their region of interest and a start date and end date for analysis. After that, the images are filtered on the basis of user requirements. Atmospheric correction is performed over these images. The water bodies are extracted. And depending upon the user input, either turbidity or chlorophyll or Secchi depth values are calculated. This is a screenshot from the tool. And on the left-hand side, we can see that there is the input panel, which lets the user select their parameters. The user can select a start date and an end date. The user has to select their region of interest and the calculation which they wish to perform. And on the extreme right, we can see the output panel, and this generates an animation as well as a graph depicting the change in water quality parameters over the study period. Using this tool, we observed the Lonar Lake in Maharashtra, which changed its color to a brownish shade on the 5th of June 2020. We compared the original satellite images with the corresponding turbidity images and observed that as the color of the lake changed to a brownish shade, the turbidity of the lake also increased. So on the right, you can observe the turbidity images. Shades of blue and green represent low turbidity, whereas shades of yellow and brown are representative of high turbidity. So on the 5th of June, where the lake changes to a brown color, we can see that the turbidity values have been very high. The same was also observed from the graph that was generated using this tool. And we can see that since the 6th of May, the turbidity values of the lake had only been increasing. A similar observation was made over the Sangam region in the district of Prayagraj, Uttar Pradesh. And we observed the two rivers in the lockdown period imposed in the country. And we could see that there was a significant decrease in the turbidity values of the rivers Ganga and Yamuna during the lockdown period. This can be observed from the turbidity images as well as from the graph that is displayed on the bottom half of the screen. The values were at their minimum on the 3rd of April 2020. We have also developed a flood mapping tool using the Google Earth engine, and this is a screenshot from that tool. On the left, we can see the input panel, and this lets the user select any region of interest within India. After selecting the year of analysis, this tool calculates the extent of land that has been inundated by water during the flood period. In the center of the map, you would be able to see a vertical bar, and this bar is known as a split panel. To the left of the split panel, you can see a collection of images from the pre-flood duration, and towards the right, you can see a collection of images from the flood duration. And this bar, this slider, can be moved left and right to analyze the difference between these two images parallelly. We will be viewing this split panel in detail when we move to the hands-on session. So this is the state of Bihar in 2019. On the left, we can see the collection of images from the pre-flood area, and on the right, we can see the collection of images from the flood season. And it can be clearly seen that the water extent in the flood season is much greater, and this extent was calculated, the area of the water extent was also calculated using this tool. So this brings me to an end of the presentation. Let us move to the demonstration of the water quality analysis tool, after which we will move to the hands-on session. So this is what the tool looks like. It is centered over India. On the left-hand side, we can see the input panel. So in our presentation, we saw the changes in Prayagraj, the changes in turbidity values in the Sangam region of Prayagraj. Now let us observe the changes in chlorophyll values over that period. So I'm selecting the start date to be the 1st of March 2020. And the end date can be 15th of April 2020. Then select calculation shows me 3 options: turbidity, chlorophyll, and Secchi depth. I'm going to select chlorophyll here. Then there's an option to select the type of ROI. So it gives me 2 options, point and rectangle. So I'll be selecting rectangle for now, and I'll be explaining the point ROI after this. Now we have to move to our region of interest. So you can either zoom into your region, or you can type the name of the place in the search bar on the top. So if I type Prayagraj and click on it, this will redirect me to my study region. Then I'll click on the Select ROI button present in the input panel and draw my region of interest on the map. Now I'll click on the Submit button and wait for the results to be generated. Now this will take a few seconds because all of this is happening in real time. Your request has been sent to the Google servers right now, and it would take a few seconds for it to be computed. So it says it's loading the results. So the results are being generated now. On the top panel, you can view a series of dates, and these are the dates on which sentinel imagery was available within the study period that we selected in the input panel. In the center of the map, a satellite image, a median satellite image has been added. Let me zoom to it. In the output panel, we can observe that an animation has been generated. Let us open this in a new tab. So we can see how the chlorophyll values of the two rivers are changing over time. The colors blue and green represent low chlorophyll values, and the colors yellow and brown represent high chlorophyll content. It can be seen that on the 3rd of April 2020, the river seems to be in a brown to yellow tone. And this can be also tracked from the chart. So this chart shows the changing values over time. And we can see that on the 3rd of April 2020, the mean chlorophyll values in the study region were at their maximum. This chart can be downloaded in a CSV or a PNG format, and the animation can also be downloaded to your desktops. Now, in the let us add each of these layers. There are 6 layers displayed on the top panel, and if I click on one of them, this is the chlorophyll layer that has also been displayed in the animation. Let us add the one from the 4th of March 2020 and the 3rd of April 2020 and observe the difference between the two. Now these layers are being added on the map. In the meanwhile, let us explore the export option available in the bottom part of the map. So the select to export button gives me 2 options. It lets me export either satellite images or calculated images. The calculated images are the water quality images that have been calculated using this tool, and the satellite images are the Sentinel images from the multispectral instrument of Sentinel-2. So I'm going to click on satellite images, and this will generate multiple links which will enable me to download these images to my desktop. So the links are being generated. This is all happening in real time. The links have been generated here. Let me click on any one of these links to see what happens. So I'm clicking on the one from 3rd of April 2020. So the Sentinel-2 image from the 3rd of April is generated, and I can right click and save it to my desktop. Also on the bottom of the map, we have a legend that displays. In the bottom of the map, we have a legend where we can see the variation in the values. We can see what each color represents. So it starts from 5 to 45. Shades of blue are in the lower range and shades of brown are in the higher range. We can also change these visualization parameters from the text boxes displayed in the bottom of the screen. And we can also do that by going to the layers and going to the setting of an individual layer. And we can change these visualization parameters from here as well. We can change the opacity of an image, the stretching values, even the palette. So these 2 images have been added to the map. The one on top is the image from the 3rd of April 2020, and it is in brown and yellow shades. And the one from 4th of March is represents bluer and greener shades, which represent a low chlorophyll content. Now this was the rectangle ROI. If I select the point ROI from the input panel, it says I can click anywhere on the map to get statistics. So I will zoom to a particular point and I'll click on a single point. And this will generate the statistics for my selected point. The statistics are being generated. So the change in chlorophyll values for this particular point are displayed to me in the form of a graph and also in the form of a list with the dates and the corresponding chlorophyll values. This point that I selected has been highlighted in the form of a red circle. So this was the demonstration of this tool. Let us move to the hands-on session and see how you can use the Google Earth Engine to build remote sensing applications. So this is what the Google Earth Engine code editor looks like. This is the area where you write your code. And to the left of it, we have the scripts tab, where all the scripts that you create are listed. Next to the scripts tab, we have the docs tab. And this is the Google Earth Engine documentation. Several objects are displayed here, and you can click on any one object in order to expand the functions that can be applied on these objects. So we can see how many functions are available for use over an ee.image object. So let me expand one of them. So this is the date function. So when I click on it, I'm given a description of what this function does. I'm also told what parameters this function requires and the return type of this function. So you can explore this data set, these docs in order to understand the different objects and the different functions that are available with the Earth Engine. Then there is the Assets tab, which lets you import your own data onto the Earth Engine. You can import a TIFF file, a shape file, or a CSV file. Towards the extreme right, you have the Console tab, and here all the print statements that you have specified within your code are displayed. To the left of the Console tab, we have the Inspector tab, which lets you determine the value of each pixel on the map. We'll explore the Inspector tab in the further hands-on session, in the upcoming hands-on examples. Then we have the Task tab, and this is used to monitor all the export tasks that you give within your code. On the very top, we have the Get Link function. This is used to share your code with others. You have the Save button for saving your code. You can also save your code by doing a Control S. We have the Run button that is used to run the code. The Reset button resets everything that is on the map and the console, all the outputs. The Apps button is used to generate apps. And below the code editor, we have the Map section, and this is where your results are visualized. You can zoom in, zoom out, you can pan the map. Several geometry options are available on the map to enable you to draw polygons or rectangles or points. This map can be viewed in the form of a map or a satellite view. On the very top, we have the search bar, and this is used to search for places. This would take me to Delhi, and similarly, I can search for data sets here. So if I type Landsat 8, it will list all the related collections related to Landsat 8. Let us view the data catalog of the Earth engine. So the Earth engine hosts climate and weather data. We have satellite imagery here. Several geophysical data sets are available. You can also view these data sets, filter these data sets to fetch exactly what you require. You can do this on the basis of the satellite, Landsat, MODIS, or Sentinel. So in order to filter these data sets, you have to type the keyword. So here, if I want data sets related to forest cover, I'll type in forest and all the related data sets would be displayed to me. So now let us study the basics of JavaScript that are required in order to get started with the Earth engine. Now, in order to get started with the Earth engine, you would need to sign up on earthengine.google.com/new signup. You do need a Gmail account for this. So any variable that is declared in JavaScript is declared with the keyword var. So followed by the variable name. So here I've declared a variable called var message, and this is a string type variable which I'm specifying within single quotes. So the variable contains the string hello world. So let us print this variable. So I'm printing it using the print function. So any parameter that is passed to a function is passed within parentheses. So let us run this code and see what gets printed. So when I run it, the console tab on the right gets highlighted. So if I click on the console tab, hello world, that is the content of the variable message, has been printed on my console. Now you can also store a number in a variable. So I've declared var number equal to 40. So this is not data type specific. You can use the keyword var to store either a string or a numeric data type. You can store a decimal number. So now I'm going to print this number, and I'm passing two parameters to the function print. One is a string and the other is the variable that I want to print. So let us run this. So here we can see that the number value has been displayed on top. This is the string that we printed, and followed by the variable with the value 40. You can also create lists on the Google Earth Engine JavaScript API. So a list is created within square brackets. So here I've created a list of 6 numbers, and I've named this variable list of numbers. Let us print this list. So when we expand this, we see that on the left there are indexes from 0 to 5. So you can access an individual element of this list by specifying the index number. For example, if I want to access the number 2 from this list, I would have to specify the index value of 3. These index numbers start with 0 and not 1. So here in my code, within square brackets, I will write the number 3 and print it. So here we go. The value corresponding to the index 3 has been printed. Also, you can create dictionary type objects on the Earth engine. The objects in the dictionary are specified in the form of key value pairs. So we have 3 keys here, A, B, and C. The key A stores a numeric value corresponding to it. The key B stores a string value, and the key C stores the list of numbers that we had just created. So let us print this object. So when we expand it, we see that the 3 keys are displayed on the left and the corresponding values are displayed on the right. So any errors, any syntax errors that you make within your code are highlighted in the code editor. So if I type var test colon a instead of equal to a, the Earth Engine would highlight this. On the left hand side, we would be able to see a cross mark indicating that there is an error on this line. You can also create user-defined function on the Earth Engine in order to make your code more modular and more readable. So here I have declared a function called sum, which takes two variables as its inputs, a and b, and it returns the sum of these two variables. Now here I've used the function sum within a print statement, and I've passed it two variables 5 and 10, and it should be able to add these two values. Let us print this and observe. So it has added the two numbers 10 and 5. Also, many built-in functions are available on the Earth Engine, and you can use them to perform calculations. But in order to use the server-side functions, you will have to work with server-side objects. You cannot use server-side functions with client-side objects. So here I have declared two server-side objects. A number in the Earth Engine API is referred to as ee.number. So I've given two numeric values 8 and 5 and generated two objects called num1 and num2. And then I have used the add function to add these two objects. So let us see the add function in the docs. Let us go to ee.number, expand it, and we can see add. So in the description, it says it adds the first value to the second, takes two numbers and returns a number. So that's what I've done here. Now I'll print these two values, the one using the function that we created, the sum function, and the other one using the add function. And please observe the difference in the time taken for the calculation of these two sums. So please observe that using the sum function, which is the client-side function, takes much lesser time than that what we achieve by using the add function, which is a server-side function. I'm going to print these two. Please observe the difference. So we can see that while the second number is still being computed, the first number has already been printed. And this difference is because the second function, the add function, is a server-side function, and these two numbers, num1 and num2, were first sent to the Google servers. The computation was performed on those servers, and the results were returned back to your browser. Of course, this process is going to take some time, and that is why it is advised to use client-side function wherever possible, and to not burden the Earth Engine with basic operations such as these. So this is almost 80% of the JavaScript that you would require in order to use the Earth Engine. So let us move to visualization and export, and let us see how you can visualize and export different data sets. So in order to import a data set to your code, you can search for the data set in the search bar present on the top. You can click on the data set. Now I want Landsat 8 surface reflectance data. So I'll type Landsat 8 SR. I will click on my data set, and here I can see a description of the data set. In the bands tab, I can see the different bands that are available. So band B2 represents blue band, band B3 represents green band, band B5 represents NIR, and so on. Several image properties are associated with each image in the collection. So we have cloud cover, image quality, a unique Landsat ID for each image, the sensing time of the image. This collection can be imported into your code by clicking on the import button at the bottom right corner. Similarly, a geometry can be imported into your code by just drawing the geometry on the map. So I'll click on the rectangle, and let me draw So when I drew this geometry, a new geometry was added to the import section of my code. So it is as simple as that. Otherwise, if you have the coordinates of your geometry, you can simply type these coordinates by using ee.geometry. So here I want to draw a rectangle, so I'm using ee.geometry.rectangle. I have passed these coordinates to this function, and a geometry would be created for me. Now let me add this geometry to the map. So to add any layer on the map, we use the function map.addLayer. I'm simply passing one parameter to this function known as geo. Here I've declared the geometry with the name var geo. And let us add this to the map. Also, I have used a map.center object, and this function centers the map around any object that I provided. So I've provided the geometry here. It should center the map around this geometry. Let us run this code and see what it does. So this has centered the map around my geometry. The geometry is still being added to the map. So this geometry has been added to the map in the form of a layer. And here we can see in the layers tab on the right, this will display all the layers that have currently been added to the map. You can select this checkbox to enable or disable the layer. Now let us visualize this layer differently. So map.addLayer takes in some visualization parameters. So here I specified a color in which I want to display this geometry. So I specified red to be the color in which I want to display this. And this is followed by the next parameter, which is the name of the layer. So by default, we saw that the layer was labeled layer 1. So by default, these layers are labeled as layer n. That means the first layer is labeled as layer 1. The ninth layer would be labeled as layer 9 and so on. But you can specify a different name for any layer. So here I am specifying the name geometry. The next parameter is false, which means that this layer would be added to the map, but by default it would be disabled. This is followed by the opacity value, which I've given to be 0.6. Now let us add this layer to the map. So the layer has been added, we can see, but it is disabled right now. So when I click on this checkbox, the layer has appeared on the map. This bar can be moved left or right to vary the opacity value. Now we had chosen the value of 10 for map.center object. This 10 is nothing but the zoom level, which ranges from 1 to 24. Let us see this in the docs tab. So in order to search a particular function, you can simply type the name of the function here. So I'm typing center, and it shows me map.center object. I'll click on it. And it tells me that the zoom level ranges from 1 to 24. 1 being the minimum zoom and 24 being the maximum zoom. So let us see what happens when we specify the minimum zoom value. So my map is still centered around my geometry, but it is at the minimum zoom level. So if I type 24, this would lead to focusing of the map at the maximum zoom level. Now we have our collection. Let us filter it on the basis of dates. So the image collection had been imported, and it is named image collection. So I'm doing an image collection dot filter date. Filter date is the function that has to be used for filtering your collection on the basis of time. So I specified two dates here. One is the 1st of January 2020 and the second is 1st of April 2020. But the second date is not inclusive. This is an exclusive value. And this range is actually 1st January 2020 to 31st March 2020. And let us print this filtered collection and see what results we get. So something is being added to the console. Yeah, it gives me an error as expected. Because right now we have filtered the collection only on the basis of time. We have not filtered it on the basis of space. And this is the entire Landsat collection. So it is a huge number. 3 months of satellite imagery for across the globe would be a huge number. So let us filter this on the basis of region also. So in order to filter a collection on the basis of region, you have to use the function filter bounds. So to the filter bounds function, you have to specify a geometry for which you want to filter the collection. So I specified the variable geo here, and let us view this output. So this gives me 6 elements. From January to March 2020, 6 Landsat images were taken over this study region. So you can expand this collection to view the individual images present in the collection. You can expand each image to view the bands that are available with the image. You can expand the properties and to see the different properties of the image. For example, the cloud cover of this image is 22.37. You can also filter images on the basis of metadata. So in order to filter images on the basis of metadata, you use the function filter metadata. This function takes 3 parameters. The first one would be the property on the basis of which you want to filter the collection. The second one would be the relational operator that you want to use. And the third one would be a value to be used along with the relational operator. So here I'm specifying that I want images with a cloud cover of less than 10. Let us print this and see how many images are filtered. So the first collection is the collection of 6 images which we had just seen. And the second print statement gives me 3 elements, a collection of 3 images. So 3 images have been eliminated. That means the cloud cover of 3 images from these 6 was not less than 10. So if we expand this, we can see that the cloud cover is 2.84. Similarly for this image, you can see the cloud cover is 9.59. So all these images have a cloud cover of less than 10. Now in order to visualize these images, you have to use the function map.addLayer. And the first parameter that we pass to this function is what we want to add. So data is my collection and I have taken a data.mean, which will take a mean of all these 3 images. Further, I specified the visualization parameters. So these are the visualization parameters. I specified 3 bands. Now I want to display this in natural color composite. So I have specified bands B4, which represents the red band, band B3, which is the green band, and band B2, which is the blue band. Further, I specified a min and a max value, and these are nothing but the stretching values. And after the visualization parameters, I've given a name to this layer. I'm calling it mean image MCC. Let us add this image to the map. The image is being added. So this is the mean of the Landsat imagery from 3 different dates. And this is the entire Landsat imagery. This is not restricted to the geometry that I had created. But in order to restrict this image to the bounds of my geometry, I would have to use the clip function. So in order to use display the clipped image, I'll be displaying it in false color composite. The only thing that has to be changed here is the bands. So I'm using the NIR band followed by the red band and the green band. The stretching values are being kept the same. Then I'm taking a mean of the collection again. At this time I'm storing it in a separate variable called mean. Then I'm clipping my mean collection, mean image on the basis of the geometry that we had created. Now let us add this layer to the map. So this is the natural color composite image which was displayed earlier. And this is the false color composite image which has been clipped to my region of interest. Now you can export these images to your Google Drive as well. For that you would have to use the function export.image.toDrive, and you have to specify a few parameters to this function. The first one would be the image that you want to export. So here I'm giving the clipped bar. Clipped, I have specified, declared this clipped variable here. Then this is followed by a description. This is optional. A folder in which you want to save your image. This is a Google Drive folder, and this is also an optional parameter. Then we specify a region and then a scale. So since this is a Landsat image, I have specified a scale of 30. And let us run the code and see how we can export this. So we see that the task tab gets highlighted and a task has been created. So this will, the description has been given here, the Google Drive folder has been shown here, and these values can be edited from here. And then when you click on the run button, within a few seconds, your image should be exported to your Google Drive. Let us see the next example in which we will observe how you can mask out clouds from a Landsat 8 image. So here I have the same data set and the same geometry. I'm centering my map over the same geometry. And then I'm filtering my image collection to contain images from the month of June. Let us print this filtered data set. So this data set has 2 images, one from the 1st of June 2020 and one from 17th of June 2020. Now using the same visualization parameters, I will add the first image to the map. Out of these 2 images, the first image, the one from the 1st of June, shall be added to the map. And I can get the first image from a collection by using the function collection.first. So here the name of my collection is data. So I've done a data.first to get the first image from this collection. Let me print this image. So the collection was printed first, and now this is the first image of the collection that we have printed. This is the image from the 1st of June 2020. Let us add this image onto the map by using the image, the visualization parameters that we had used in the previous code, and specifying a name to this layer. Let us observe the cloud cover in this image by going to the image properties. We see that this image has a cloud cover of 54%. And this is also evident from the image. where we can see that the top half of the image is covered with clouds. So more than at least approximately 50% of the image is covered in clouds. So how do we mask out these clouds? So I've created a function here called mask L8, and this uses two bits 3 and 5 of the pixel QA band in order to mask out the cloud and the cloud shadows. So let us expand this data set, observe its bands, and we can see that a pixel QA band is available in which each bit is representative of what this pixel represents. So bit 3 indicates that this pixel is a cloud shadow pixel, and bit 5 indicates that this pixel is a cloudy pixel. So here I've used bit 3 and 5 in order to mask out these clouds. I have joined these two masks here, and then I have updated this mask over my image using the update mask function. This mask L8 function is passed the image as a parameter. So when we pass this image to this function, it will mask out the clouds over this image, and it will return the masked image back, which I am storing in the variable masked image. Now let me add this masked image to the map. So here, this image has been added and all the cloudy pixels have been masked out. This as compared to the original image, we can observe that many cloudy and cloud shadow pixels have been masked out. So this is for Landsat 8. Every data set will have its own bands, and each data set might have different fields representing the cloudy pixels and the cloud shadow pixels. Let us see how we can calculate NDVI using the Google Earth engine. So I have the same collection using filter date. I have filtered it from the 1st of January 2020 to 31st of March 2020 and filtered it on the basis of the geometry. So let us print this data set. It should contain 6 elements. Yes, it contains 6 elements as we had seen earlier. Now by default, this data set is sorted in ascending order of time of image acquisition. So we can see that the first image is from the 9th of January 2020. It says 2020-0109, which means 9th of January. And the very last image is from 29th of March 2020. Now if we want these images to be in reverse order, we can sort this collection. So in order to sort the collection, we use the function collection.sort. And we specify the metadata property on the basis of which we want to sort this collection. So system time start is a property of every image in the Landsat 8 collection. If you go to the properties, we can see that the system time start is a property available here. And false indicates that this collection should be sorted in a descending order. So if I print this sorted collection, so we have the filtered data set and then the sorted data set. So the filtered data set has the images. The first image was from the 9th of January, whereas in the sorted by time, sorted in descending order of the time, this data set contains the first image from 29th of March 2020 and the last image is from the 9th of January 2020. So it has sorted my images in the descending order of time. Similarly, I can sort my images on the basis of cloud cover. So I'm again applying a data.sort over the cloud, and I'm using cloud cover as the metadata property on the basis of which I want to sort my collection. And let me print this value, this collection. So the sorted cloud cover collection should have images that are sorted in increasing order of cloud cover. So the very first image is from the 10th of February 2020. If I expand this, I can see that the cloud cover is 2.84. Whereas for the last image, if I expand this, I can see that the cloud cover is 87.2. So this has sorted the images in ascending order of cloud cover. Now I'm adding the first image from the sorted time descending collection onto the map. That means that this would be the latest image, that is the image from 29th March. So the layer is being added on the map. And this is displayed in false color composite. Now let us calculate NDVI over this single image. So there are three methods which we can use to calculate NDVI. So the first of them, so we can select a single band from an image by using image.select. So I'm selecting two bands, B5, which corresponds to the NIR band, and B4, which corresponds to the red band. And the formula of NDVI being NIR minus red upon NIR plus red. I'm simply using the subtract, add, and divide functions of the Google Earth Engine to create my NDVI image. So I've done a B5.subtract B4 dot divide B5 dot add B4. Now, since the normalized difference is such a popular formula, the Earth Engine has provided a built-in function for applying normalized difference over images. So this function takes two bands as inputs. So I've specified band B5 and B4 and simply performed an image.normalized difference in order to calculate NDVI over this image. So this is the second method. The third method is by using image.expressions. So here I can specify any expression that I want to evaluate over an image. So I've written x minus y upon x plus y, and then within the curly braces I have specified what x and y mean. So x is the band B5 of the image, whereas y is the band B4. So let me add one of these to the map. So I'm adding the NDVI 3 here. The image.expression can be used for much more complex expressions. This is just a very simple formula. So let us add the NDVI on the map. I've specified a palette here, a white and green palette. This palette can be a collection of hexadecimal HTML color codes, and this list can be much longer. I've just specified two colors here. The layers are being added to the map. So this is the false color composite, and this is the NDVI that has been computed over this image. So you can check or uncheck a layer to enable or disable it. But what if we want to view these layers side by side? So the linker comes to your help here, because the linker enables you to link two different maps. Here I have taken two instances of UI.map. So this section where the images are being added is known as UI.map. So I've taken two instances of UI.map. I am calling one left map and I'm calling the other right map. So then I've created a linker which links both the maps. That means that if I zoom in on the left map, the right map also gets zoomed into. And if I move the left map, the right map also moves accordingly. Then I'm adding both the left map and the right map to this root. And then I'm adding the different layers to the maps. So to the left map, I'm adding the original image. To the right map, I'm adding the NDVI image. So here I'm adding the NDVI 1, the one that we calculated using the add and subtract and divide operations available with the Earth engine. So let us run this code and see what happens. So we have two maps here, one on the left and one on the right. And on the left map, the FCC image has been added. On the right map, the NDVI image has been added. So if I move my left map to the left, the right map also moves. If I zoom into my right map, my left map also gets zoomed into. So this is useful when you want to parallelly analyze any two images or any number of images. Then you can, let me demonstrate the split panel that we had seen in the flood mapping tool during the course of the presentation. And the split panel is instantiated by using UI.split panel. It takes two panels as inputs, first panel and second panel. So I've specified the first panel as the left map and the second panel as the right map. And I've added the split panel to the root. This is, so when I run this, so we can see a vertical bar in between. This is the split panel. On the left of the panel, we have the FCC image. And on the right of the panel, we have the NDVI image. And this panel can be moved left and right to parallelly observe the changes in any two images. Now let us see the map function and let us calculate NDVI over a set of multiple images using the map function. So here I'm using the same image collection and I filtered it from the 1st of January 2020 to 31st of March 2020, filtered it on the basis of my geometry. And further I am filtering it on the basis of cloud cover. Let me print these two collections on my console. So collection 1 is filtered by time and region, contains 6 elements. Collection 2 is further filtered with respect to cloud cover and it contains 3 elements. Now in order to compute NDVI, we need to first create a function that calculates NDVI. So here I've declared a function called NDVI calc and it computes NDVI using the normalized difference function provided by the Earth engine. I specified the bands B5 and B4 as its inputs and it returns the NDVI image. Then here I'm using this function over my collection along with the map function. So map is a function which takes another function as a parameter. So I am applying the map function over my collection. My collection is named data. The variable name of the collection is data. So I've done a data.map and I have provided the NDVI calculation function in the brackets, in the parentheses. So let me print this collection. So the NDVI collection contains 3 images because we had provided it 3 images as an input. We had provided it this filtered by cloud cover data as the input. So it contains 3 images. Each of these images has a single band, which is the NDVI band. So we can expand this and see that each of these images only have a single band associated with them. Now let us add all these images to the map. So there are 3 images, 3 layers are being added to the map. One is from the 10th of February, one is from the 26th of February, and the third one is from 29th of March. These 3 NDVI images are being added to the map. So this is the NDVI from the 10th of February. This is the one from the 29th of March. And this is the one from the 26th of February. So I have calculated NDVI over just 3 images. These can be any number of images. So this brings me to an end of the hands-on session. And the Google Earth Engine not only provides access to vast amount of data and processing power, but it has widely simplified global scale analysis as well. So I would encourage all of you to get started with the Earth Engine. I'm sure all of you will thoroughly enjoy it. We'll move on to the question answer session after this.